Here is a modern inference accelerator. Hundreds of trillions of operations per second on the datasheet. And here it is running a chat conversation, one user, one token at a time. The arithmetic units are mostly idle. Not because the chip is badly designed, because during single-user decoding, the machine is not computing. It's waiting on memory. And the traffic it's waiting on is mostly one thing: to generate the next token, a transformer has to attend over everything said so far. Rather than recompute the keys and values for every previous token each time, which would be quadratic and absurd, it stores them. That store is the key-value cache. Its size is straightforward. For a model with L layers, H key-value heads, each of dimension d over a sequence of T tokens, the cache holds on the order of 2 times L times H times D times T elements. Note the T. Everything else is fixed by the architecture. T grows with the conversation. Double the context, double the footprint, and double the bytes you must read per token. Grouped query attention helps. It shrinks H and it's standard now, but it changes the constant, not the growth. And here is the part that surprises people. At the context lengths users now expect, the KV cache routinely exceeds the model weights, both in how much memory it occupies and in how many bytes must cross the memory bus for every single token generated. Quantizing the weights is the thing everyone does. At long context, it's optimizing the smaller number. This is a roofline argument, and it's worth being precise about it. Batch 1 decode has terrible arithmetic intensity. Very few operations per byte moved. That puts it deep in the memory-bound region, nowhere near the compute roof. The TOPS number on the datasheet describes a ceiling this workload never approaches. So the binding constraint isn't arithmetic. It's bandwidth and the energy cost of moving data. The industry knows this. Vendors are provisioning separate silicon for the context phase of inference. NVIDIA Rubin CPX is a public example. When companies start building distinct parts for a phase of a workload, the problem is real and it is expensive. The question is where to spend silicon to fix it. There are two established approaches, and both work. Both also have a cost worth naming. 1. Compress the cache in software. Quantize the KV cache to low precision. KV, KV quant, gear are representative. Per group scales, careful handling of outlier channels. These are good techniques and they deliver substantial memory savings at minimal accuracy cost. But look at where the work happens. The quantizing and dequantizing run on the accelerator's own compute units, using the accelerator's own bandwidth. You are spending the exact resource that is already the bottleneck in order to relieve the bottleneck. It also needs model-side integration. 2. Move the computation to the memory. Processing in memory, compute in memory, D-matrix's digital in-memory compute is a commercial example. That's a genuine answer to the data movement problem, but it's a whole architecture commitment. You are redesigning the core of the machine. It is not a block you can license and drop onto an existing memory port. So there's a gap. Software compression is contained but taxes the scarce resource. Compute in memory frees the resource but isn't contained. What if the compression happened somewhere else entirely, not on the accelerator, not inside the memory, but on the wire between them? Put a small fixed function block directly on the memory data path, between the accelerator's DMA and its external memory controller. KV blocks get compressed on the way out to memory and reconstructed on the way back in. 4 properties follow, and they're the whole argument. 0 accelerator flop. Dedicated logic does the compressing. The tensor units never see it. The scarce resource stays untouched. Line rate. The engine is sized to match a memory channel. For n lanes, a bus width W bits and clock F, throughput is n times W over 8 times F bytes per second. That's a design knob, not a fixed number. Scale n to saturate whichever memory controller the licensee actually has. Transparency. To the accelerator, it looks like ordinary memory. Reads and writes. Compression is an implementation detail behind that interface. No model changes, no attention kernel changes. Recency awareness. This is the KV-specific lever. A token's value to the model decays with distance, so recent tokens can be kept at high precision while distant ones are compressed harder. A general-purpose memory compressor has no way to know that. This one does. What it costs in return: a few pipeline stages of read latency and some silicon for tables and lanes. For a workload that is waiting on memory anyway, that trade is favorable. There is one genuinely awkward problem, and it's worth being honest that it's the crux. Compression is variable ratio. Some blocks compress well, some don't, which means a compressed block is not at a fixed stride from its neighbor. A hardware DMA addresses memory by computing an address. Base plus index times stride. If blocks are variable length, that arithmetic no longer finds anything. You could track it in software, but then you've reintroduced exactly the accelerator side cost you were trying to remove. So the engine maintains an on-chip structure that lets a hardware DMA address variable length compressed blocks with no software bookkeeping. That capability, making variable ratio KV compression usable by a hardware datapath, transparently, is the engine's principal architectural novelty. How it's implemented is not in the public paper, and it's not in this video. That's disclosed under NDA, pending a Freedom to Operate review. I'll tell you what it achieves, I'm not going to tell you how, and I'd be suspicious of anyone who did before their FTO opinion came back. It's an AXI and memory boundary drop-in. Native KV blocks in over a streaming interface, with a small sideband carrying sequence, layer, and token indices so it can judge recency without parsing payloads. Licensee's memory protocol on the other side. Standard register block for configuration. It's parameterized soft IP, bus width, formats, quantization group size, number of recency tiers, whether the entropy stage exists, lane count. One core spans an edge so see through a data center part without a redesign. But the single most important adoption feature is duller than any of that. A first-class bypass mode. Logic on the critical path to DRAM makes integrators nervous, and they are right to be, so you integrate it disabled. Prove datapath equivalence against your known good baseline, then enable compression. Combined with a self-checking equivalence test that de-risks the one property an integrator actually cares about, turning the block on never changes functional results, only footprint and bandwidth. If you've ever integrated third-party IP, you know that's the feature that decides adoption. Now the part that matters most for judging any of this. This is an architectural and positioning argument, not a measured result. The quantitative envelope, compression ratio, accuracy impact, added latency, area, depends strongly on process node, memory technology, and model family. It has to be rederived per deployment. Figures carried over from prior architectural analysis are credible engineering estimates. They are not certified results, and I'm not going to put a number on screen as though they were. Accuracy in particular. Aggressive compression of distant tokens needs characterizing against real KV traces before it belongs on a datasheet. Not assumed. And on novelty, KV compression has substantial prior art in software, and memory path acceleration has prior art in hardware. The defensible contribution claimed here is narrow and specific. Inline, line rate, recency-tiered compression with transparent hardware addressing of variable length blocks. Any assertion of novelty is subject to a formal freedom to operate opinion, and that opinion isn't in yet. That is the honest state of it. One extension worth naming. For automotive, industrial, and robotics edge inference, the same engine can carry safety instrumentation, error-detecting codes on its on-chip tables, duplicated control, integration into a fault collection path, so it can support an ISO 26262 argument as a safety element out of context. That variant exists because long context inference is arriving in vehicles and factories, where it usually works is not an acceptable property. The engine is available for licensing as functional safety instrumented soft IP, the KVCE Lite, STD, and Pro variants at circuit design. Space. The architectural paper is on Zenodo, the DOI is on screen and in the description. Detailed microarchitecture and sign-off data are under NDA. Long context inference is a memory problem. The KV cache is the traffic at its center. Compressing it in software works, but taxes what's already scarce. Moving compute into memory works, but rebuilds the machine. A small block on the memory data path is a third option, and it's one you can license rather than build. Next time, attention itself derived from scratch.